time, at the end of last lecture, right, we have talked about we could use binary search to compute the square root of any number, right? We said we can convert it into a functions. When we drive these functions like this, the only thing we need is finding a point that is negative and finding a point that is positive, because the function is continuous, so we can find the root in the middle. So we ask you to do it offline if you have time. Right, let's do it together. How can we making sure we can find out which one is the root? All right, so let me hide it. Right, so what we are trying to do is we want to implement a new version, for example, square root of 2. Right, this is our goal. And this function should return a double because square root is typically a double. And then we have our input n, right? And we said this one, we need a range, right? A range that is becoming smaller and smaller. And initially we said we could use the range. Starting point is 0 and with the number of n, right? Let's make it n equals to 2. Here is n, here is n, right? As long as this n is maybe greater than some number, we can making sure the fn is a positive number, right? So in here we have the starting position, the end position, right? As long as we are making sure that f of x equals to x squared minus n. This is our function. And we are trying to making sure the start is negative and the end is a positive. As long as this condition satisfies, we know the root is in the, then the root is in the range of start to end, right? By using binary search, we could do something like now int double. Let me make it double and a double. So we can find out who is in the middle. In the middle, we could say start plus end divided by 2, right? Then we are trying to evaluate is middle times middle minus n. Is this one negative or positive? If it's negative, it means we need to search in the right part, right? Then we need to search in the right part, return my square root, and start becomes middle, and end becomes end, right? And else, we are trying to search from the left side, start with start, end with middle, right? This is the typical recursive thinking, right? We are trying to make the range smaller and smaller. We are cutting the range by half, and each time we are searching for a smaller and smaller range. So we haven't deal with the special case, right? We said the recursion need a special case to stop. Otherwise, it will continuously calling these two recursion functions. It will be infinite recursion. So we have to specify when do we stop. We said, all right, as long as these two guys are close enough, right? Close enough, then we could return either of them. Let's return start. It'll be fine, right? So this would be a typical way to write a recursion, right? Special case, then making the problem smaller and smaller. So when we run it, you can see it can successfully compute this square root of 2, right? 1.4, something like that. So this one can also be generalized. As we can see, we are defining a function like this, right? We could define a function called f. Our input is x. Then we are trying to return, let me give it another n. We are trying to return x times x minus n, right? Then this one can be f of middle, right? Middle and n. We are making this one more general, right? It can apply to any function like written in here, as long as it is some function that can that is continuous, right? We will be able to find out the square root. So this one could be, for instance, how about x to the power of 3, right? How about x to the power of 3? As long as this one is satisfies start is negative and is positive, we will be able to find out the root, right? It is 1 point something. How about 4, right? We could continue. We can construct this function in any form, right? As long as we can find out someone start end, that is one is positive, one is negative, then we can find out the root. And as you can see, we could make this one general, right? So this is the way we write. And there's another thing that is a little bit tricky here is you are asking someone to use your function like this. It is sometimes a bad scenario because whenever people want to call my square root, they instead of calling this way, they typically like to call in this way, right? So what we would write is a helper function. We will learn later, but let me show it here. We would typically say, okay, how about we have this one as an interface, right? Using this one as an interface, then we are trying to return, call this one helper, my square root helper. This n, 0 starting position, and position n, right? We could do something like this. And this helper becomes here. Right, in this way, we are making sure the user is happy and our recursion function is happy, right? We are creating some helper function that is start with some point and end with some point. So what's another benefit about it is instead of putting 0 and n, right? You could find a way to get the start and end such that fx is less than 0 and f start is less than 0 and f end is greater than 0, right? You could implement some way in here and make this one start, make this one end, and start calling these functions. So we are trying to making sure this one is no longer a square root helper, right? It becomes a root helper. We are trying to find out the root of any function f. We are trying to find out the root of any function, right? But in the future, we know we could also make the f a parameter in here. But that's another story. So any questions on it? I believe if you guys practice it offline, you will have some questions, right? No? This one is not so difficult, right? All right, let's go to our slides. Where's our slides? So for what we have learned, we learned that the most difficult thing about recursion is the thinking process. How can you think recursively? Instead of in the old way of doing just sequentially, right? Everything sequentially. Thinking recursively requires you to abstract your problem. Becomes a smaller and a smaller problem, right? So we will, for instance, using this as an example, we want to test if a sentence is a palindrome. So what is a palindrome? If you look at the second sentence, right? A man, a plane, a candle, Panama. A matches A, right? M matches M, then A matches A, right? If everything is symmetric, if the whole sentence is symmetric, we call this one a palindrome. We call it a palindrome. So this is a function to test if a sentence is a palindrome or not. So in our OJ system, I believe we have an exercise, right, to test if a string is a palindrome. So we are making sure the problem is simpler. It's something like the ROTOR, right? This one is this guy a palindrome. We are trying to implement something. So what is the interface for this function? It is called is palindrome, and we are taking a string s and returning a boolean. If it's true, means s is symmetric, s is palindrome, right? Otherwise, we say s is not a palindrome. So how can we making sure think recursively, right? Writing a recursion to solve this problem. So first one, we are trying to making sure the problem is smaller, right? Like the binary search, we are trying to make the range smaller. In the factorial, we are trying to make the n smaller, right? Each time it's n minus 1. So how about this one? This one, we have several ways, right? We can remove the first character. We can remove the last character. We can remove both the first and last. We could remove a character in the middle. We could cut in half, right? There are many possible ways to do it. So because this problem is so easy, it's very hard to explain why do we do the first way, right? But anyway, we will give you an example to show the possible ways. There are many possible ways you could do. So in this one, we know, okay, maybe we should remove the first and last character, right? Because we are checking if this one symmetric. So we just comparing the first and last, then remove them from the original string, and it becomes a smaller string. So the second step is assuming, right? We are assuming we already get the solutions from simpler questions. Remember here, we haven't implemented our function yet, but we just assume we already get the result from simpler inputs, right? How can you combine them into the result of a large problem? That is very difficult. But this one is not that difficult. This one is saying, okay, if assuming I remove the first and the last character, it becomes OTO. If I have a function that returns a true or false for OTO, right? If I already know if OTO is palindrome or not, how can you, from this result, to construct the result for rotor, the original strings, right? So that would be the problem of the second step. How can you combine the solution from smaller one into the original problem, right? This is exactly here. If I already know the root from the left-hand side, or if I know the root from the right-hand side, how can you construct the result for the large problems? But this one is obvious, right? It's just a return. There's no extra work. But for the factorial, right, we are from the simpler solution times n is the larger solutions. And for this one, it's also very easy, right? We can test if we already know the smaller string is a palindrome, then we can compare the last and the first letter. If they matches, we are done, right? So last one is the finding the solutions for the simplest inputs. So what is the special case for this recursion? So if it's an integer, we typically write something like 0 or 1, right? If it's a string, we typically write a empty string, right? If it's a shape, we say, okay, what if it's no area? If it's a range, right? What if it only contains one element, or the range is small enough, or the range is invalid, right? They are the special case when should we stop? So also sometimes you might want to investigate a slightly larger, right? Instead of empty strings, how about contains one character, right? How about two characters? Sometimes we want to test, is our case already cover all these kind of scenarios? You need to test that. So if you forget some of the special case, you might get into an infinite recursion, right? You cannot stop the program, right? So let's look at what's the solutions. Yeah, by the way, we haven't finished this yet. So there are a few things we could consider for the special case, right? Such as empty string. We could use this one as a special case. If it's empty string, we return, for example, return true, because empty string is always a palindrome. How about a one character? Right, one character is also palindrome because it's always a symmetric. Do we need two characters as a special case? That is a typical question, right? Do we need two characters as a special case? Because we already know the process, comparing the first and last, removing them, and return the result for the substring in the middle. So do we need two characters? The answer is no, right? Because we already have the test for empty strings. If we already have the test for empty strings, we don't need the test for two characters, because it's a general case. You can remove the first and last, and you will get an empty strings, right? So it is included in the recursion process. And you should also ask, do we need the single character scenario, right? Sometimes, and especially when the length of your string is odd, right? How about it's odd? How about it's even? You need to consider both scenarios because you are removing 2 characters at a time. So you need to consider the special case when there's only 1 character or there's no character. So go back and think about it. Why do we choose these last 2 scenarios as a special case instead of 3 scenarios, instead of just 1 scenarios? You need to think about that. Let's see the implementations. So the first line says, if the length is less than or equal to 1, it means either empty or just 1 character. We just return true because it's always palindrome, right? And next is oh, by the way, because we haven't learned strings, this is the function to get the length of a string. And this is the function to get the substring, the position starting from 1, right? And this is I believe this is the length. So you can check that in the check it online, search for string, substring, and it will give you these functions. And we will see how we can implement it not using these kind of functions. But anyway, let's go back to recursions. So this is a special case, right? This is a special case we have dealt with. Then we get the first character and the last character, right? The first character and the last character. Then we compare them. If they are not equal, we immediately return false, right? If they are equal, we can get the result for the shorter substring, right? By removing the first and the last. And then we can test, is the one in the middle a palindrome, right? If in the middle is a palindrome and also first equals to last, the output is true, right? If the substring in the middle is not a palindrome, we know this string S is not a palindrome, right? This is the result. This is the result from a simpler questions. And the remainings are how to construct from a simpler question, simpler result, construct from simpler result to a more complex problem, right? Like this one. This one might not be obvious. Let's do a complex example. This one is really complex. This one, returning a permutation, right? It's not such a problem for a beginners, but anyway, let's do it. Let's practice. How can we generate this one? So assuming our input is 1 to 4, 1 to 4, we are trying to list all the possible permutations. List all the possible permutations. Like the 1 to 4, 1 4 2, 2 1 4, 2 4 1, right? You need to list all of them. So if there are n numbers, if there are n elements, how many possible permutations are there? 2 to the power. Is it 2 to the power of n? One solution to the power of n. Another one choice, 2 choice. Let's do it. If n is 1, right? If n is 1, how many possible permutations? Just 1. If n equal to 2, how many permutations? If it's just 1 and 2, another permutation is 2 and 1, right? 2. If n equal to 3, this is n equal to 3, total is 6. What's the pattern? Yeah, n factorial, right? So this is the total number of permutations you need to compute. Let's do it. So first, think recursively. How can we construct a simpler problem? If I give you 1 to 4, can you construct a smaller one such that our function could return our result? maybe I should do it in here so that the Zoom could see it. Wait, it's not writing. It's weird. Okay, this one works. So if my input is 1, 2, 3, as my input to, for example, my permutate function. Think recursively. How can you make the problem smaller? How can you make the problem smaller? Pardon?
1, 2, and the
Yeah.
last 3.
Yes, yes. You are trying to make the factor smaller. If you try to make the factor smaller, for instance, I temporarily remove 3 and keep it in some place. For example, keep it in A, all right? Then we are assuming with a smaller one, how can you think recursively? We assume our function already successfully implemented and will give us the result. Will give us the result for a smaller problem. Let's just assume it did, right? Let's do it by hand. So what will be the output? The output would be, it will return 1 and 2 and 2 and 1, assuming it returns a 2-dimensional array, 2-dimensional vector. All right, let's just assume it successfully gave me the result. So your question is, starting from the solution for a smaller problem, how can you construct the solution for a large problem, right? So that is the difficult part about recursion. How can you start from the solution from a smaller problem, construct a solution for a large problem? So for this problem, it will be first I will get each element from my smaller solutions, right? First, let me get 1 and 2 out. So now I have 1 and 2. In order to construct the permutation for the original one, I still need this A, right? I still need this A equal to 3. The question is, how can we combine them and make them a valid solutions? So a simple way is insert 3 into different positions, like 3, 2, 1, 3, no, 1, 3, 2, 1, 2, 3, right? For every solution in the smaller one, I create 3 more solutions. And for the second one, I create 3 more solutions. And there will be total 6, right? 6 solutions. And also there will be no overlap because the order in the smaller problems, the order is different. And I maintain the order. I just put A into different positions. So 1 and 2, their relative positions are maintained. So there will be no overlap. There will be no duplicate solutions if you do it in this way, right? You can insert a 3 in here, 3 in here, 3 in here, right? Because 1 and 2, their relative positions don't change. So there will be no duplicate solutions, right? So you know the whole process. Let's do it in here. Let's assume, comment them out. Let's have a factor of integer, right? Let's call it VC 1, 2, 3. What we are trying to is get a permutation. Permutation is a factor of integer. Let's just call it P, okay? And I call the function permutate. And then at the end, we were trying to print this P so that we can see, are we doing it correctly? All right, so this is the whole process. What we need to implement is, one is permutate function. Second is print function. Because print function is easier, so I would like to print first. do the print function first. Let me copy that. Because I want to save some space and I don't want the program to change it. So I make it constant reference. It's called VC. So next part will be tedious. I less than VC the size plus I for J from 0, J less than VC I size plus J. Then I'm trying to print VC ith row, jth column, separate by empty space, right? Separate by empty space. So let's test this one first, right? We said whenever we write a function, test it. Okay, we test it. It will be quite easy. Just to give some initial values, 1, 2, 3, 3, 2, 1, and let's see if it can print it, right? Write a function, then test it. We forget about the new line, right? So let's do it. Maybe make it easy to see. A new line, then no. The ending bracket, then a new line. Here we see out a starting position, right? Let's see, is it nice or bad? Yeah, it's good, right? This printing format is good. So after finishing this print function, we can keep on working with our permuted functions. So let's copy it here. No, I should copy the whole line. So from now on, we can forget about this print function because we already tested, right? Then we can do the permutate because our returning value is a 2-dimensional array. This is the return value. Then our input is a 1-dimensional vector. And let's keep it constant so that we don't modify it. Let's have another one called this one a result, right? Result. And at the end, we are trying to returning this result. In the middle, we said we are trying to make this factor smaller, right? We are trying to make the factor smaller. How can we make the factor smaller? Remember, if it's 1, 2, 3, we are trying to create a solution for 1 and 2, right? So we are trying to remember our A, which is the last element. Let's call it factor dot back. Back means the last element. It could also be, for instance, factor dot size -1, right? It's also fine. This is the last element. And then we are trying to, let's just copy that because we want to modify it, right? We want to modify this factor. And then let factor pop back, right? Now we are remembering the last element. Then we are making the factor smaller. 1, 2, 3 becomes 1, 2. And then we are trying to returning the result. The smaller result equals permutate of your factor, right? So this part, I would say construct a smaller factor by popping the last element, right? And here is construct the result from smaller result. So next part is a little bit complex, right? But at least in here, we have already assuming the permuted function could work and returns us the smaller result, right? Which is stored in the smaller. So how can we get it? We said we are trying to access each element of smaller, right? So we are trying to access each element in our smaller result. This is the smaller result, right? Let's go back to here. This guy is our smaller, right? This guy is our smaller. And we are trying to get each element from our smaller, which is 1, 2, and have our A such that they can combine and construct a sum of the results, right? So what we are trying to do is we have smaller, we have the A. A is the last element of the original factor. How can we combine them and generate, for example, many results? Let's just copy them into our result. Make it some functions so that you can test. Let's call it, what should be the name? Should be add 1 to each position. All right, let's call it this way. Let's implement this one. Just call it add to each position. Add to each position. Yeah, that will be good. Let's implement this one first. Let it be void. So what does it do is, assuming we have a vector and some integer number A, then we are trying to get the result, right? And this one should be a reference because we want to modify this result. And when it is returned, and we can get the final result. So let's see how it is implemented. Let's first make some comments. What does it do, right? Let's assume factor is 1 and 2. A is 3. We are trying to add a bunch of factors. 3, 1, 2, 1, 3, 2, and 1, 2, 3, 2 result, right? This is our goal. Result is our return value, actually. And we are trying to, starting from 1, 2, and 3, we are trying to create 3 factors and push them into the result, right? So this is our goal. So we are making sure our problem becomes easier and easier, right? Instead of considering the permuted function, it is really complex. We are trying to implement a simpler function first. It's called add 1 element to each position of your vector. So how can we implement this one? So this one should be easy, right? This one, let's just iterate through all the positions of vector I less than vector size. And here, if the vector dot size equal to 2, right? If it's 1, 2, this for loop only iterate for 2 times. But indeed, we are requiring 3 elements, right? We are requiring 3 factors. So this one should be less than equal. If the, let me repeat, if vector size is 2, we are returning 3 factors, right? 3 elements. So that's why we are making this one less equal so that we can iterate 3 times. All right, so how can we, so each round we are adding A to factor in the ith position, right? If I equal to 0, we are inserting into the position 0. If I is 1, we're inserting position 1. If I is 2, we are inserting position 2. So that is our goal. There exist some functions in vector library called insert, but I don't want to confuse you here because that function requires the iterator. Right. Let me show you the iterator version first. So it basically do is factor.insert factor.begin plus I and the value A. This is the insert function already implemented by the library. So what it does is insert, give the position. Position is the beginning position plus ith offset, right? If it's beginning plus 0, if the end, beginning plus the size. Then insert the element you want to insert. Let's first test it first. And after you getting the factor, right, you will push it into the result. All right, let's assume this insert could work. What's the problem of this function? What's the problem of this loop? Can anyone see the problem here? There are some problems in here. What's the problem here? Assuming this one successfully inserted the A into ith position of vector, what's the problem of this for loop? Mm-hmm. 对, but I to the fourth position is correct. Let me test this. Yeah, that's correct. Because your factor is keep increasing. Let's test this problem. Let's test this function, right? Sometimes you would write your code in this way. You think it's correct, right? You just insert into the ith position. Then you push back. It seems correct. Let's test this one. How can we test one function, right? Whenever you write a function, test it. Let's test this guy. Let me have another one called this P, which is the result. Let me call it the result so that it's easy to see. And let factor be 1 and 2. Let's test this function by calling it, right? Adding 3 and to it and print it, right? Not print P, print result, right? In here, we are testing this add to each position function. Add VC, right? 3 adds 3 to each position of 1, 2, and keep the result in result, and then we print this result. Let's see what will happen. Wait a minute, I might forget something. Add to position, right? It's calling add to position less than. Yeah, also that's the problem here, right? Let me see how can I make it show here. VC is increasing, then we are pushing back. Wait a minute, why it never stop? It's weird. Let's do a debugging, right? Let's do a debugging. So the problem I want to mention here is we start with I equal to 0, right? I equal to 0. Then we are trying to insert into the first position, A into it. It should get 3 to 1, 3, 1, 2. It has no problem. VC, the size is 3. It becomes 3, 1, 2, right? Then we insert it into our result. Result contains one element, which is 3, 1, 2, right? The first element. It's a two-dimensional array. It contains just one element. First element is a vector. Vector contains 3 elements, which is 3, 1, 2, right? How about next round? When we go into next round, vector size becomes 4. It will becomes these 3. The first 3 is indeed the original 3. The second 3 is the newly inserted 3, right? So it will be a problem here, right? You guys can see it. Yeah. So that will be the problem. Another problem is vector.size. Because we are increasing this one each round, increasing the size each round. This size is also increasing, right? Each time when you increase one, vector.size also increase. So it will be an infinite loop, right? So that is the problem here. So whenever you write a function, you think this one is simple, right? But indeed, there may be some errors. So remember to isolate them, then test them. Otherwise, if you put this one into your code, you will think, okay, this part, of course, I don't have any issues with this part. So you will ignore this one and start testing the others. Then at that time, there will be some problems. So anyway, so let's go back here. Indeed, you need some copies, right? So let's make this one a const so that no one could change it. Make it a const to avoid some errors, right? Errors like vector.size. No one could change this vector.size. But in here, I cannot insert what should I do is, how about I create a new one, right? I copy it, create a copy to it, call it a temp. Then in temp, I would insert it, right? At the end, I would insert the temp. So in this way, I'm not changing the vector dot size, and each round there will be a new vector created. That is starting from the original one, 1, 2, right? So after implement this, test it again. I should delete these breakpoints, let it finish. Right, now it can work. You have already tested this add to each position function. The input is 1, 2. You are inserting 3 to it, right? Inserting 3 to the first location, second location, last location. So now you have tested this add to each position, this function. Now you can ignore this one. You can ignore this one because you already tested. So you can trust it, and you don't have to worry about it. So let's go back to our original one. Yeah, print P, right? So this one will be the final one. Let's see, is there anything missing in here? I have already implemented adding A to each position of a smaller element, right? A smaller result. Is there any place that is missing for a recursion? Yeah, the starting position, the special case, right? If we don't have that, it will just keep running. So what should be the starting case? Let's do the special case, right? Because we care about vector's size. The special case could be the easiest one. How about vector dot size is just 1, right? If it contains only one element, the permutation is very easy. If there's only one element, let's make the result. Oh, all right, we need the result. How about result dot pushback your VEC, right? Then return your result. So this could be the special case. When there's only one element in the vector, you don't need to permutate, right? Because there's only one possibilities. So just push back into your result and return it. After done with this, test it. Let's see, is it working or not? Right, 6 of them, it seems working. 3 in different positions of 2, 1, then 3 in different positions of 1, 2. Right, so also you can test the 4, right, with size 4, and test it like this, right? Yeah, it should be 24 possibilities. You can keep on and on to do it. So for this kind of problems, it's a little bit difficult to implement in for loop. You can try to convert it into for loop. You can do that. It's not extremely difficult, but it's a little bit difficult to convert it into a for loop, right? Think about it. How can we convert it into a for loop? The idea is similar. We first, whenever we read one, right, getting the result from the previous one, iterate through them, then adding them in different positions, one by one. So that would be the thinking process. But anyway, you can go back and try to implement it. It will take you some time to make it correct. And by the way, if we don't want to use this insert function, right, can we implement some function that is doing insert? Can we implement some function that is doing insert? Let's put it here. Can we implement a function called myInsert? All right, let's give you this and the position I and the element A. Let me call it A. Right. So what we are trying to implement is insert let's assume VEC equals to 1 and 2. If I equal to 0, I will generate, and A equal to 3, I would generate 3, 1, 2, right? How can we implement such a function? And if R equal to 1, you will returning 1, 3, 2. How can we implement this kind of functions? Keep pushing back, right? Yeah, it's correct. Keep pushing back the values. For instance, if what I can create is, for instance, I can call it this one. Let this one be our result. Return our temp. In the middle, we need to put 3 in the ith element. So originally, if we want to make a copy, right? If we want to make a copy, what we would do is like this, temp dot pushback VCI. So in this way, the result and the vector will be exactly the same, right? We just keep pushing back every element. So how can we making sure someone is in the middle? So we just push to another I, let's call it position. I might not be a good parameter. So we just keep pushing until the position. Then we push back A. Then we keep pushing back the remaining. Starting from position to vector dot size, right? This is someone we should be able to implement. How can we insert element in the middle of a vector, right? This will be quite easy. First, keep the first part, then push back A, then push back the remaining, right? Now this A is in the position of your vector. So let's test this one. Insert. Let's test it in here, right? How about in here? Let me put here my insert vector position I, and the value A, right? If it's correct, it should work. Let's see. Yeah, it seems to work. Let me make this one 3 so that it's easy to see. Yeah, it's working. But for you, you should test this function independently instead of put it back into add to each position function and test it. You should test this one, right? Just this function. You should just test this function. But because of the time issues, I just tested it together. But you should test it independently. And also, this one can be simplified, right? Can be put in here. This temp is not needed. Yeah, it's the same. It could work. Right? You can keep simplifying them. And as you can see, for someone who think about this, making your code smaller by removing these functions, right? They would think, okay, there's only just 2 lines. How about I making them in here, right? How about I just copying this part into this part, right? A beginner typically tend to do that. They think they don't feel like modularize these functions, right? So their code will be inside a very gigantic functions. If we do this way, this testing will be very hard. So I would suggest making them independent. All right. So any questions on it? In some days, the large companies, they typically using permutations as the interview questions, but these are not the kind of questions they would give. What they would give is if I have duplicates, like 1 comma 2, comma 2, comma 3. Can you give me the permutations? If there will be duplicates, can you give me the permutations? So for that problem, right, it's kind of interview kind of problems. They would ask you to write by hand. That's typically we do in the interviews. All right, so you should be able to implement this one by hand. Any questions? No? All right, so this is a question we have done, and input-output type, you should be able to know it. And can you write a loop for it? Yeah, it's a little bit difficult, but you can try it. All right, so we have talked about this one, right? Recursive helper functions. There are sometimes there are two advantages of using a helper functions. First one is making the user friendly, right? User will only need to know what they only need to know is calculating the square root, right? They don't want to know how recursion is happening in your side. They don't want to know the details. They only want to know this kind of things, right? If I give you some number, you give me some number. And indeed, what you are doing is you are create some helper functions like this one, right? A helper functions like this. It is requiring the range or the, we say it should be containing the size of the problem, right? Which problem are you trying to solve? The range from start to end, calculating the root, right? It will help you in making the problem smaller in recursions. So that is the helper, right? Sometimes we call it helper functions. And if we use the palindrome as an example, let's look at the palindrome. It is, we said it's inefficient to construct a new object every time. So if you look at the palindrome, as you can see, we are trying to create a new string in here, right? If your string is very, 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 very long, you are creating, for example, if the size is n, you are creating n divided by 2 numbers of substrings. It's creating a new string. You are copying all the characters. You're copying all of them. So it will be a nightmare sometimes if the problem is too large. Copying is time consuming. So how can we get rid of these kind of scenarios, right? When you are constructing a smaller problem, but each time you are wasting some of your space or time doing this of copying. So what we can do is, rather than creating a new string, we can do something similar to our finding the root, right? Like the range. You can specify where are we now. So we can adjusting the start and end parameters for a functions. So let's look at, do we have the function? Yes. So for instance, if your interface is palindrome, you give me the input as string, I will return to you true or false for these palindrome functions, right? If it's true, it's a palindrome. It's a false, it's not a palindrome. And in here, we can call a helper function that is specifying the range. So 0 to the end, right? Similar to the binary search, 0 to the end. So in this function, you are trying to move the pointers by the start and end, right? Instead of copying a new string, you just move them. Let me draw it here. So if it's ROTOR, right? If you want to test, is this guy a palindrome? First, you can have a start, you can have an end. You are testing the characters start with end. Then you can call the function again, is substring blah, 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 your S. Now start +1 and end -1, right? In this way, you don't need to copy this string every time. You're just calling it, making the range smaller and smaller and smaller. But you need to specify when to stop, right? When the start end meets, or when they only have one characters in the middle, then you will be, it will return true or something, right? So this is a helper function. As you can see, we get rid of the copying the strings, right? We are also making sure this interface is user-friendly. The user use your functions is quite easy. They just call s. They don't need to give you 0. They don't need to give the length, right? Because they don't want to care about the details about how you implement your functions. So that is the benefit of using a helper functions. All right, so it's just about the style indeed. So, so we say when we are trying to design a recursive solutions, we typically do not want to worry about the multiple nested calls, right? When we are calling with the start and end, we don't care about how it is implemented using, for example, smaller one. The smaller solutions, we try to ignore how it is implemented, like this permutation, right? Like the permutation. If we think all the problems together, that would be very difficult. But I want you to ignore how this one is implemented, right? Giving a smaller factor, how it get me the smaller result, get rid of it. Don't worry about how it is implemented. Just assume they will give you the result. Otherwise, your thinking process will be very, very difficult. All right, so that is a some suggestions. Another problem will make you maybe a little bit confusing is called mutual recursions. So for now, we just a function calling itself, right? But mutual recursion is you calling another function is calling you. So you just do mutual recursion, doing this over and over and over again. So for this one, we use an example. Here, we're trying to develop a program that can compute the arithmetic expressions like this one, 3 plus 4 times 5, right? You should be able to give preference to multiply, right? It should compute 4 times 5 first, and then plus 3. If it's have parentheses, it should do 3 plus 5 first, then 3 plus 4 first, then times 5, right? And also you should consider some complex problems like this, right? If there are multiple parentheses, how can you deal with that? So indeed, what you are writing is, indeed, we call it a compiler. So your compiler knows numbers, knows multiply, knows plus and minus, right? You're writing a compiler. Your compiler should know how to construct the computing process. So let's do it. So this is the one we are trying to formulate the problem. So don't ask how we can do this, but just assume it's here, right? Just assume it's here, because in order to understand it fully, you need to learn the compiler class. But anyway, assuming the whole thing is an expression, right? Either anything could be an expression. And expression is constructed by terms, and also terms plus terms, terms minus terms, and keep going. And each term is constructed by factors. Can be factors or just the factors, or factor times factor, factor divided by factor. And each factor is constructed by expressions with parentheses or just numbers. So if you think about recursion, you can see it is a recursion, right? Expression calls term, term calls factor, factor calls expression. So it's 3 functions calling it in a loop. It will be infinite loop until there will be a special case in here, the number, right? When the factor is a number, the recursion stops. If the factor is also an expression, this recursion continues. It's called a mutual recursion, right? It's about 3 functions calling each other, then becoming a loop. It's very, maybe it's very hard to understand it fully. If you think about this one, it might give you some examples, right? So assuming it's 3 plus 4 times 5. If it's 3 plus 4 times 5, what we are trying to achieve is we want our calculator to compute 3 times 5 first, then a plus, right? And we said everything is an expression. Everything is an expression. The whole thing is an expression. And we said expression is constructed by terms. expression is not constructed by factors. Expression is constructed by terms, or term plus term, term minus term. So when we trying to split this expression, it can split into term plus term, right? It is split into term plus term. And then term can be constructed by just a factor or factor multiply a factor, right? Can be a factor or just a factor or factor multiplied by a factor. And as you can see, until now, we have constructed something like a tree. In the future, we know it's a tree, but it also tells us how to compute the order, right? As you can see, if you trying to get the value of this expression, you need the value for the left term. Left term is easy, it's 3, right? And also the right term. Right term is 4 times 5. And until here, we have already defined the order we should use. We should do multiply first, then a plus, right? We should do multiply first, then a plus. It's not defined by any rules. It's defined by the order of function calls, right? It's defined by our grammar. Grammar says expression is constructed by terms of term plus term, term minus term. That's why this plus is evaluated at the end. It's not evaluated first, it's evaluated at the end. And the term is constructed by factors, right? And then terms can, inside the term, you can consume this multiply. If you look at the right-hand side, expression can be expressed as term or term plus term, because the whole thing does not contain a plus in the middle, right? So this one is just a term. Then term can be a factor multiply a factor, right? A factor multiply a factor. And a factor is constructed by a parenthesis with some expression, right? And now we have defined the order. This one should be calculated. It should be calculated 3 plus 4 first, then do a multiply. So this is how we can define the order of computing. The order of computing is defined by this grammar, right? Expression is constructed by terms. And you notice term don't contain multiply or divide, right? Then term is constructed by factors, and factors are constructed by expressions. So if you can implement this one correctly, the order is maintained by this rule. The whole thing defines the order of doing a multiply and doing plus and minus last, and doing multiply and divide first. So we can define 3 functions called expression value, term value, and factor value. And then inside of the expression value, we can have a term value and also plus or minus. Let's just look at the code, how it is implemented, right? Evaluation value, we first get the result from the first term, left term. Remember, when we call term, it will also call factor. When we in factor, we also call expression itself. So it's a mutual recursion. So here is the term, right? In term, we will call factor value. In fact, we will call expression value. It's a mutual recursion. This is expression value, right? It calls term value. Term value calls factor value. Factor value calls expression value. So you are doing recursively, assuming, let's do it again. In recursion, don't focus on the details, focus on, just assume it can work, right? Let's just assume term value will give you the first term. Let's assume that. Ignore about the details. Let's assume you can get the value for the first term. Then how can you construct the whole values, right? You will look at the next operation, next character. This one is called a peak. Peak means don't consume it. Don't consume it. Just look at what is your next input. Just look at the next input, but don't consume it. Don't eat it, right? It's still in your cin. Next time, if you want to cin, you will get this OP. But let's first look at it. If it's either plus or minus, we know we will have another term, right? If it's a plus or minus, we will have another term. If it's not a plus or minus, we know we can stop. We can stop this expression because expression only contains term and a plus or minus. If it's not plus or minus, we can stop. we can just evaluate this term. And go back and check what is seeing.peak means and also seeing.get means. Seeing.get means consumes the next character, right? And if it's plus or minus, we can get the value for the next term, right? Get the value for the next term. And if the count operation is a plus, we return the result. If it's a minus, we return the result like this, right? Minus values. So as you can see, we ignore how term value is implemented. We just assume it is there, right? It is there, and it will give us the correct output. And then we construct from the term value function and construct the result for your whole expression. So that is the total idea. Similarly in here, right? If it's a term, we know it's constructed by factor multiply a factor, right? So you are assuming factor value works. Just get the result and check peak or check the next operation. If it's a multiply or divide, you construct another factor, then compute the result. If it's not multiply or divide, it means the end, right? You should stop your term evaluation and you will stop it. Just return it. As you can see, it calls the factor value. Factor value, we just assume it can work. And how can we implement the factor value, right? It is constructed by either numbers. If it's numbers, we do it in here. Either numbers or if it's a parenthesis, right? If it's a parenthesis, we just consume this left parenthesis and also the right parenthesis. And in the middle, there are some expressions, right? As you can see, we just assume expression value can work. Don't care about the details, because if you want to care about details, expression value will call term value. Term value will call factor value. Factor value will call yourself, right? So it will be a recursion. It's very hard to understand. Just assume they can work. Then if you construct all the rules correctly, you are making sure this problem is solved. So one more thing is, are we making the problem smaller, right? We said as a recursion, we are trying to making sure the problem is smaller and smaller. In here, where is making the problem smaller? Our problem size is indeed inside of the Cin. Inside of the Cin. Your whole expression is your problem size. Now, each time you just eat one character by one character, right? And you are making sure your problem is smaller. When your Cin is done, you are done. All right, so another good example in here is here, what this one is doing. What this one is doing. This part of code. Line 10 to 14. This is a while loop. What it's doing? Yeah, I know what you mean. It's changing characters to a number, right? To a decimal number. So remember, every C is a character, right? If you convert this one to integer, it's ASCII code. How can you convert it into a number, right? So for instance, if I do it in here, what I want to do is, let me do here, convert character to int. Let me call it this way. So it should be a character array, right? Let's call it S. So your input is something like this. Convert character to integer 1, 2, 3. So your goal is to convert a string input 1 to 3 to 123, right? How can we do it? It should be a very good example of something in the exam, right? Writing a function that's converting a string containing only characters, only digits to an integer number, right? This one can be, yeah, students ask me what kind of problems can we have in the exam. This kind of problem can be in the exam. How can we do it? We can have, let me call it something, the result. At least we need to iterate through all the characters, right? Int I equal to 0, I less than the size. What is the size of a string? String length, right? Plus I. How can we construct it? There could be a simple way, and let me think how to say it. Yeah, there should be a straightforward way and a not straightforward way. Let's do it in the not straightforward way. Maybe we should do the straightforward way first. All right, assuming input is 1, 2, 3, right? What we are trying to get is 1 times 10 to the power of 2 plus 2 times 10 plus 3. Right, this is what we are trying to do. So we should have, let me put the result equal to 0, then result plus equal. What is the character? Should be S of I, right? What is the value? Value is this guy minus the ASCII code of 0. ASCII code of the SI, if it's character 1, should have some ASCII code, right? Present it. If you minus 0, it is integer 1. Integer 1, then times the power of 10 to the power of something, right? What is this something? What is this power? If I is 0, what is the power? 10 to the power of, remember, if this is the 1, 1 is the position 0, it's the power of 2, right? If it's 2, it's power of 1. If it's the last element, it's power of 0. Yeah, string length minus 1 minus I. This should be the power. Then return result, right? Let's test this one. I'm not sure if it can work. Include, because I need string length, I need the math. Is it math or C math? It doesn't matter. Let's see if it can work. Yeah, it can work, right? It's outputting 1, 2, 3. But you don't know if it's string 1, 2, 3 or integer 1, 2, 3. Let me copy it. Int a equal to this one and this. All right. Yeah, 1, 2, 3. Let's give a 0 here. 1, 0, 2, 3, right? This kind of problems, it's indeed not that hard, right? It's only a few lines of code. Indeed, the most important part is in the middle, just one line, right? So these kind of problems are something that we might have in the exam, because I already told you, so this one will not be in the exam, but similar, right? So I said this one is the straightforward way. How about not a straightforward way, right? Let's have another version, which is implemented in the slides. Indeed, let's call it version 2. How can we do it? We are trying to avoid using the power function. We're trying to avoid this power function. So let me do it in this way. 1, 2, 3 is indeed 1 times 10 plus 2 is 12, right? Whatever you have get times 10 plus 3, right? How about 1, 2, 3, 4 times 10 plus 4, right? Let me make it here correct. Power of 2, 3 times 10 plus 4, right? How can we implement this one? It seems like a for loop, right? Each time times 10 plus your current one plus times 10 plus your current one. So what it will do is result equals to result times 10 plus S of I. Hey, wait, it's not equal. It's a plus. All right. This is the way we implement. So either this or this, it's fine, right? Either of them will work. Let's try. Let's test it. Let's test this one. Wait, it's not correct. Oh, wait, I forgot to minus the 0 because otherwise it will be the ASCII code, right? Otherwise it will be the ASCII code. Run it, you get the result, right? Or you can create a breakpoints here, look at what is the result. First, result is 0. Next, when it gets 1, this one becomes 1, right? Next round becomes 1, 0, because my input is 1, 0, 2, 3, right? And the next round it becomes 1, 0, 2, right? And next round it becomes 1, 0, 2, 3, right? So this is the example we have shown in the slides here, right? Results equals 10 times the results plus C minus the ASCII code of 0, right? So the C minus 0 is indeed converting strings digit to an integer digit, right? All right, so do I have time to finish the efficiency? Maybe yes. Let me see how many of them. All right, yeah, by the way, any questions on it? No? All right, so let me talk about something about the efficiency. Efficiency is something you can test offline. So has anyone tested the Fibonacci recursive way with a large number in your own computer? Test it? All right. So the Fibonacci we talked about last time, right? When I test it in my machine, if I am giving a large number, for example, 100, my machine will just keep running. It will never stop. So that is something you should get noticed because the recursions are sometimes it's quite slow, especially for this kind of problems. For a function call, you convert it into 2 function calls, right? So if you look at the whole process, this is the function we write, right? Fibonacci n equals to Fibonacci n minus 1 plus Fibonacci n minus 2. And you can put a output in here, right? You can check how many times this guy is executed. Let's do it. Let's do it together. Let's do it here. See out. See out. All right, let me call this function Fibonacci of 10. When you run it, you will see many outputs, right? First time entering n equal to 10, and then n equal to 9, 8, 7 until here. Then entering n equal to 2, you return, right? Entering n equal to 1, return. Then exiting n equal to 3, and then go on. As you can see, some place it's entering 4, 3, 2 again, then entering 5, 4, 3, 2 again, right? you will see, indeed, you only need 10 times calling, right? If a Fibonacci of 10 might be you only need to know Fibonacci of 1, 2, 3, 4 until 9. But indeed, it's calling many, many times. So go back and check this one offline, right? And we will come back to this one next class. Right. Thank you.